Hello and welcome to the Vault of Truth YouTube channel. This is Flat Earth Proof 159. Earth-like planets that support life are impossible. So a while back in one of my previous Flat Earth Proofs, we discussed how impossible it is for life to emerge on a given planet even if all of the correct conditions exist, with the biggest problem being going from a chemical soup to even the first single-celled organism with complex DNA. Scientists to this day still cannot determine how that leap happened. In this video, however, we are going to look at how improbable it is for all of the right conditions to exist at the same time on a given planet in the universe. We are going to calculate the probability of an Earth-like planet forming in the midst of a very destructive and inhospitable globe Earth cosmos. So let's jump into it. We start here with the four major types of galaxies that they claim are found in the universe. You have elliptical, spiral, lenticular, and irregular galaxies. 3 of these types are suitable for life, but one of them is not. And that will be your irregular galaxies. The reason for this is that irregular galaxies are shaped that way because they are undergoing either a collision with another galaxy, or they are being stretched by centrifugal forces from being slung around another galaxy or galaxy cluster, or they are being ripped or deformed by some strong gravitational influence or a strong dark matter push, and this would cause pretty much all of the solar systems within these types of galaxies to destabilize, with planets being flung out all over the place, either away from their parent stars altogether, or sent crashing into each other, or sent crashing into their parent stars. So at this level of the analysis, we start with our first probability multiplier of 3 out of 4. Now we jump to the next level of the analysis, and we are looking at the habitable zone of a given galaxy. It just so happens that only 10% of the stars in a galaxy fall within this zone. The outer regions of a galaxy are too metal poor to support life, and the interior regions or center regions are far too active with far too much radiation. And this increased radiation comes from things like increased numbers of supernova explosions, increased numbers of magnetars, etc., etc. So we get our next probability multiplier of 1 out of 10. At the next level, we're now looking at suitable stars for hosting planetary life. Out of all of the stars that you see on this list, only 2 make the cut, which is your orange dwarfs and yellow dwarfs. Some people try to contend that red dwarfs could be a suitable type of star, but the problem with these types is that they are too dim, they don't put out a lot of heat, and this would cause the habitable zone of the orbits of life-bearing planets to have to be too close to the star, which would not only tidally lock the planet to the star at a much more rapid rate, causing one side of the planet to burn and the other to freeze, but it would also put the planet at a much closer range to deadly solar flares and radiation bursts. Also, the much dimmer light would make photosynthesis much more difficult, so really these types of stars don't really work. The giant-sized stars are too violent, they release far too much radiation, and then some of your other stars on this list are too cold, far too violent, such as your magnetars and your neutron stars, or have far too strong of a gravitational field, such as your black holes. Orange dwarfs and yellow dwarfs make up 17% of stars in the universe, so that gives us our next probability multiplier of 17/100ths. Now there's one other fact that needs to be mentioned regarding sun-like stars, and that is that 50% of these stars are joined together in a multiple star system. These types of systems are not conducive to planets with stable orbits due to the complex forces involved when you're talking about multiple stars orbiting around each other. And of course, I go further into depth on that in my proof where we discuss the 3-body problem. So now we get the next probability multiplier of 1/2. Okay, now let's look at the next filter. According to mainstream science, only 40% of sun-like stars contain rocky planets. And remember, a rocky planet is what we need in order to facilitate all of the different variables needed for life. Gaseous planets, such as Jupiter, for example, fail to provide many of the mechanisms needed for life to start, or even to thrive. Gaseous planets also don't provide a firm location on which to stand, and this would cause things to fall to a greater and greater depth until finally being crushed by the immense surrounding pressures. Also, pretty much all of the gaseous planets that have been analyzed contain toxic or hazardous chemicals in their atmospheres, such as methane or ammonia. So we get our next probability multiplier of 2/5. Now that we finally arrived at our suitable solar system, we run into our next filter, and that is the habitable zone within the solar system. We are going to look to our own solar system to come up with the ratio of how big this zone is relative to the radius of one of the larger bodies in the solar system from the Sun, Pluto. The habitable zone within our solar system sits within a distance between 0.75 AU and 2 AU. Pluto orbits at a distance of 40 AU on average. So using this, we can get a ratio as to what percentage of an average solar system is habitable, the region where temperatures are not too hot and not too cold. And we arrive at our next probability multiplier of 3.1%, or 31 divided by 1,000. The next thing you need in order for a planet to have life is a guardian gas giant that sits in an orbit further out from the central star, in order to protect the life-bearing planet from extinction-level impacts that originate from large asteroids or comets. As it turns out, only about 10% of Sun-like solar systems have this kind of setup. So we get our next probability multiplier of 1/10. The next variable we need on our ingredient list is a moon of significant size. You need this in order to maintain a stable tilt of the planet, mild weather, steady seasons, slower spin, and a tidal pull that is crucial for nutrient mixing, which is a key factor for life. It turns out that only 5% of planets have a moon of significant size. So we get our next multiplier of 1/20. The next thing that you must have on your life-bearing planet is a strong magnetic field. The planet has to be protected from deadly solar radiation and deadly cosmic rays. To find the correct probability multiplier, again, we're going to look to our own solar system to count how many of the rocky planets have a magnetic field. Mercury has one, Venus does not, Earth obviously, Mars no, and Pluto no. And yes, I realize that Pluto is technically no longer a planet, but it's still a significantly sized body, with a small chance that at some point it could have had a magnetic field. So when we look at these planets, we see that 2 out of the 5 have a magnetic field. And so we get our next probability ratio of 2/5. Another major ingredient that you need is one that many are well aware of, and that is liquid water. According to mainstream science, only about 35% of discovered exoplanets contain liquid water in significant amounts. Scientists have also recently determined that it takes a significant amount of water on a planet to adequately host life. So you couldn't have a planet the size of Earth, for example, with all life being supported by a body of water no bigger than the Great Lakes. That just wouldn't cut it. We need the massive Pacific and Atlantic Oceans for all of this to work. So we get our next probability multiplier of 7/20. Now we get to the core chemicals needed on a planet to sustain life, or to create life. You need carbon because it's the backbone of organic molecules and structural compounds. You need hydrogen to make water and to form hydrocarbons. Nitrogen is critical because it builds amino acids, proteins, DNA, and RNA. Obviously, oxygen is needed because it's a driver for metabolic energy and water formation. You also need phosphorus because it's involved with cell energy transfer and forms the backbone of DNA and RNA. You also need sulfur for protein structures and cell enzymes. The following percentages you now see show what percentage of exoplanets these elements have been found on. Carbon is not that common at 12%. Hydrogen is obviously common because it's very abundant in the universe overall. So we have 65% for that. Nitrogen is pretty rare at 8%. And then oxygen is extremely rare. And this is because without a mechanism to replenish it, oxygen reacts with many different chemicals and elements and combines with them. You need a large amount of plant life, for example, to convert carbon dioxide into oxygen. You can also get oxygen temporarily from water evaporation, but unless you have a relatively thick, stable atmosphere, that temporary oxygen can get stripped away into space pretty easily. And then, of course, you have planetary outgassing that can happen from volcanic activity, which can release oxygen from pockets under the ground. So far, there's only been 3 exoplanets with any kind of oxygen content discovered to be present. So that gives us a pretty small ratio against the 6,300 exoplanets that have been discovered thus far, according to mainstream science. And that's what gives us the 3 divided by 6,300 ratio there. Phosphorus seems to be pretty rare at 8%. Sulfur, though, on the other hand, seems to be pretty abundant. And of course, we see that even within our own solar system. Now, I want to pause here for a second to make something clear. Obviously, I don't believe in the globe Earth cosmos or our solar system as it is presented to us by the mainstream. So when I'm stating all of these mainstream facts about their model, I am simply just stating what they are presenting to us. I certainly do not believe in planets, and I absolutely do not believe there are 6,300 other worlds out there that have been discovered. But again, the main point of this video is to take all of this information that is presented to us and use it against them to shatter the globe Earth model. Now, does this mean that every scientist who is studying all of these things through telescopes or laboratories or with various instruments is in on the agenda to lie about the shape of the Earth? No, not at all. Most of them just believe this stuff. They are taking real measurements and getting real data, but it's how they are interpreting that data and their strong internal desire to try to fit all of this data to the globe model that is the problem. For example, with the exoplanets here, they say they have discovered 6,300 other planets with all of these chemicals identified in connection with these planets. In reality, though, all they have seen is tiny dots of light orbiting slightly bigger dots of light deep in the sky through telescopes, and through spectroscopy have seen certain patterns in the light emissions that lead them to believe certain elements are connected with those objects. But since these scientists are so overzealous to find other planets in their globe Earth universe, they jump straight to one conclusion, and that is that they found countless other worlds. They don't stop to think that these objects could be different kinds of charged crystals embedded in a firmament, or that they could be pockets of gas trapped within bubbles of energy, such as bubbles of plasma or electricity. And we've seen this same pattern of misinterpretation over and over. It's the same problem we get with the Michelson-Morley experiment and other interferometry experiments, where they claim to detect the spin of the Earth, but yet don't detect any of the other motions because they claim a Lorentz contraction is taking place due to the made-up wacky theory of relativity, causing all of our instruments to warp and bend in just the right amounts to where we can't see those movements, instead of just coming to the simple conclusion that the Earth doesn't move. Or when they discover the gravity model is off by 97%, they invent fictitious material called dark matter and fictitious energy called dark energy, neither of which have ever been discovered or created in a lab, so that they don't have to throw out the whole gravity model, which would actually threaten the very globe Earth itself. So mainstream science has been hijacked by a massive series of gross misinterpretations and pseudoscientific attempts to patch together a broken model. It doesn't mean that the whole world scientific community that believes in the mainstream is in on the agenda. The number of people that are in on it are actually a very small percentage. And they are paid extremely well and have positions of extraordinary power, neither of which they would ever give up to blow the whistle on any of this stuff. So anyways, back to the subject matter at hand. So now with all of these chemical percentages, we obtain our additional probability multipliers shown there at the top. There are some additional trace elements that we need on our planet, such as magnesium, which powers chlorophyll in plants and drives enzyme functions. We also need iron and zinc, which help drive electron transport and metabolic reactions. We also need calcium and sodium to maintain cellular balance signaling, and structural integrity. The Globe Earth believers get pretty lucky with some of these trace elements because they happen to be very abundant, with magnesium, iron, and zinc showing up in 100% of exoplanets, and calcium and sodium showing up in 90%. Now down here on the bottom we have 2 additional planetary conditions, one of which, liquid water, we've already discussed. However, there's a new one that we need to add into the equation, and that is the chemical Goldilocks balance. So scientists have recently discovered that during core formation of a planet, there has to be a moderate amount of oxygen already present. If you have too little oxygen, phosphorus gets trapped in the core. If you have too much, nitrogen escapes into space, which makes the surface sterile. You can imagine that hitting this balance would be a pretty rare thing, and you would be correct, as it shows up in only 1% of exoplanets. So we get our 2 additional probability multipliers of 9/10 and 1/100. The next attribute that our life-bearing planet needs is a slightly tilted spin axis. This gives you moderate seasons, atmospheric balance, and oceanic circulation. Without any tilt, the poles would freeze and the equator would bake. You also wouldn't get any atmospheric circulation. Now again, like I've said before, I am simply stating the facts that the mainstream is giving us. I obviously don't agree with the concept of a tilted spin axis on a ball planet with an atmosphere creating seasons and atmospheric circulation, and I even cover some of that in one of my previous proofs. But again, the whole point of this video is to take all of the ingredients they claim are needed for a life-bearing Earth-like planet, and then seeing where the probability falls for that planet to exist. Okay, moving on. So if the planet has a high tilt, they claim you would get extreme temperature swings and climate chaos. So their claim is that a healthy planetary tilt for supporting life falls between 10 and 35 degrees. We can look to our own solar system to get our ratio, and we find 4 planets that have a tilt between 10 and 35 degrees: Earth, Mars, Saturn, and Neptune, which is obviously 50% of the planets in our solar system. So that gives us our next probability multiplier of 1/2. Okay, so we just got done talking about the tilt of the spin. Now we need to talk about the speed of the spin itself. The planet cannot spin any faster than roughly 10 to 16 hours per rotation. If you go any faster than that, you get centrifugal breakup, extreme Coriolis, hyper-intense jet streams, and cloud shredding. The slowest that the planet can spin is 1 rotation roughly every 100 days. Any slower than that and you get thermal collapse, as well as loss of the magnetic field, because you no longer have a geodynamo effect happening in the core. Of course, if you've been watching my channel, you know that the geodynamo effect has never been proven or replicated either in a lab with a physical model or with a computer model. Again, though, we're just going through and collecting probabilities from the mainstream here. So with that spin range now confirmed, we can look to the solar system to get our ratio of the number of planets that have that spin range, and we find that 5 of the 8 planets have it, with those planets being Mercury, Earth, Mars, Uranus, and Neptune. The reason why I left Saturn out at 10 hours and 33 minutes is because I just took the average of 10 to 16 hours to come up with a limit of 13 hours instead of 10 hours, and so that's why Saturn is not in the list. Okay, we move on with our probability multiplier of 5/8. All right, we've come to the last variable that is needed for a Earth-like life-bearing planet, and that is plate tectonics. This is needed for the carbon cycle, temperature balance, stable oceans, fresh minerals, and then the feeding of those fresh minerals into the oceans. And of course, you need fresh minerals to fuel life. And of course, plate tectonics are kind of nature's way of recycling the surface of a planet. It turns out that this planetary attribute, however, is very rare and is only found in 1 out of 500 exoplanets. All right, so now let's take all of the probability multipliers that we've collected and let's multiply them together. When we do that, we get 5.55 times 10 to the minus 20th. And then if we divide 1 by that number, we get a 1 in 18 quintillion chance of finding an Earth-like, life-bearing planet out in the universe. Now, they tell us that the total number of possible planets out in the universe is 10 to the 22nd power. So we can take that number and divide it by the number of planets you would have to go through in order to get to an Earth-like planet. And we come up with only 555 Earth-like planets in the entire known universe.
So you're telling me there's a chance? Yeah!
And that's exactly the attitude and behavior of globe defenders. When they hear that there's a chance that there could be 500 Earth-like planets out in the known universe. So before everyone starts jumping around in excitement like Jim Carrey there, let me give you a quick reminder on how vast they claim the globe Earth universe is, and how impossible it truly is to ever find an Earth-like planet in it. They tell us that there are roughly 2 trillion galaxies in the known universe. Based on the probability we calculated, you would only find one Earth for every 3.6 billion galaxies. Let that sink in for a second. And also remember that each galaxy contains on average billions of stars. We can firmly conclude here that the hostile globe Earth universe is incapable of producing a planet like Earth with all the ingredients needed for life. So the fact that Earth even exists, and we are all here as a form of complex life, along with countless forms of vegetation and animal life, is a disproof of the entire globe Earth and the globe Earth cosmos. Because according to their model, neither us nor this planet should exist.